Good morning, everybody. Welcome to another exciting morning of Chem 1105 with your host, me, Dr. White. I've already had a busy morning. I've been out to Menards, uh, sort of public service type thing. Best friend of mine who moved back from Indiana recently, like last week, got a dehumidifier from Menards. I don't get any kickbacks from them. And I went out this morning and bought one. They're on sale until the end of the month. Plus, you get a 50, yes, $50 rebate from ComEd if you live in ComEd area, which I believe all of you do. So if you know anybody who would like to dry out your home, even though my air conditioner, I think, does a good job, but I think this will help a lot more. All right, let's get started. First of all, over the weekend, I sent out the individual points per problem for test three. A lot of you did real good. Some of you need to do some extra work, a lot of extra work. And with that in mind, sometime this week, I think maybe tomorrow and also maybe Thursday, I'll go through some of those problems again, along with the three-step mold problem. You need to know how to do those. Hint, final coming up. All right, couple of things. First of all, tomorrow well, today I'll finish it, but tomorrow I will go through the acid-base problem set. A week from today and later tomorrow, sometime I'll post it before Wednesday's class, probably tomorrow sometime afternoon, I will post information about test four. Yes, it's coming up a week from today. 2 weeks from today is the fun. Where does summer go? Went Zoom. I hope you're having a good time. I am. But anyways, I'll post the information about test four. And don't forget, do your labs. Over the weekend, I spent a lot of time making sure I got everybody's, hold on one sec. Something popped up on my screen from one of my software apps on my computer here. But anyways, I spent a lot of time hunting down, make sure I had everybody's scores or hand tests you hand, not tests, labs you handed in. Hand in labs. They're 10 points. You don't hand it in, 0 points. All right, what we'll be doing today is one, I'm going to go through test number three answers. Next, I'll go back and I'll go and finish the acid base chapter. And then you're going to be on my home court. Really, we're going to talk about organic chemistry. Yay. So exciting morning. Let's get going. Now, you should never, ever be penalized for a mistake I make in grading on a test. If you see a mistake I made, and the most common one is if you're supposed to get 3 points, I gave two, you're supposed to get four or more, maybe I gave you less. Do not ask now, why did I take off points? Email me and I'll regrade to whatever problem you want me to on your test or problems. Hopefully I didn't make those many mistakes. Usually I don't, but last time I looked, I don't walk on water unless it's frozen. Even then I stay off it. And check. Uh, and with that, let's get going. All right. Now, I've got a question. If I were in your shoes, I'd ask, Dr. White, what grade am I getting right now? I'd say, good question, and I'll tell you. So I will. Method A. Everybody see method A on your screen right now? Thumbs up, people. Thank you. All right. Method A. Take the sum of your three test scores and divide it by 3. You'll get the number X. If you look at my syllabus, you get 80 to 89, you're getting an 8 right now. 70, 80 to, yeah, greater, let me start again. 90 to 100, you're getting an A if that's what X is. 80 to 89 B, 70 to 79 C, 60 to 69 D, below 60 F. That's assuming you've handed in all your labs. If you're not, this doesn't work. You subtract what labs you don't have a score from this test score. Then there's a method B. And method B, y is equal to the sum of the two highest of the three test scores divided by 2. And you'll get a number. If that number is 90 and above, you're getting an A, 80, 89 B, 70, 79 C, and 60, 69 D, below 60 F. That's not what I want. And that's how you do it. It's assuming you've handed in all of your test scores. I just want to check something real quick. All right, I just checked it real quick. All right, any questions so far? If you didn't get to the good score on, thank you, Ray, on test number 3, listen to some advice from me. And that is do the extra credit project. It's 10 points. It's like adding 10 points to one of your test score. It's due a week from today, if I remember correctly. It's optional, but as a public service to you from me, email before you submit it, email your extra credit project to me. I will look it over. If there's anything wrong, I'll tell you this is what you need to change. That way, if you put any effort into it, and it doesn't take that long, you should be able to get 10 bonus points, which will help a lot of you. So do the extra credit project. Also, don't forget to hand in your labs. All right, let's get back to acids and bases. We're talking about pH scale, which is probably one of the most important things of, not the most important things, I'll teach you this semester. Remember, pH equal minus the log of the hydronium ion concentration. And if the hydronium ion concentration, H3O plus, equals 1.0 times 10 to the minus X, which is my special gift to you, it doesn't have to equal that, then minus the log of 1.0 times 10 to the minus X. When this is 1.0, then the pH is X. Now, you should know for pH, get the message? The pH scale goes from 0 to 14, 14. In between is 7. At 7, you have neutral pH. That's when the hydronium ion concentration equals hydroxide. Below 7, we call that acidic. Hydronium is greater than hydroxide, and above 7, we call that basic. You should know that. The closer to 14, that looks better. The more basic. The closer to 0, the more acidic. Things that are acid taste sour. Lemons and lime contain citric acid. You bite into it and you go, ooh, was that tart? That's because there's an acid in there. The pH is less than 7. Why? Chem 1105 reason is the liquid in your and my stomach. I don't want to get personal, but I will. Why is the pH less than 7? Because it's acidic. There's an acid present. I won't ask this on a test, but it's a great miracle of life to me personally that I have cells in my body that make hydrochloric acid, HCl, to make the liquids in my stomach acidic. Now, water dissociates, and because of that, there's a dissociation constant, Kw, named after me, I wish. Is hydronium ion concentration times hydroxide equals 1.0 times 10 to the minus 14. All right, let's go through the following. What is the pH of a solution if the hydroxide OH minus concentration is 1.0 times 10 to the minus 10? And is it acidic, basic, or neutral? Good question. What are we being asked to find? pH. What are we given? Hydroxide ion concentration is this. But pH, and this is an important information, test number 4, is this, which I don't have. How do I get this? Well, an important information, you have this. And in order to get this, when given hydroxide, guess what? You need 2 steps. Step 1, convert OH the hydronium ion concentration. Step 2, convert the hydronium ion concentration to pH. All right, let's do step 1. And the only thing we have to work with is this. But we also have this, which we're given. We want to solve for this. How do we get it alone on one side? We get rid of this. How do we do that? Divide by it, because anything divided by itself equals 1. Cancels out. And now this divided by this equals 1. So I have this. I can put in this value, which I have. Let's see if I have the right number. I do. So I'll pick up my calculator. Not. I can do this one in my head. Am I done? No, I have the hydronium ion concentration. I need the pH. So now I'll do step 2. If I can spell it. pH is minus the log of the hydronium ion concentration. We just figured that out right here. And now, remember when this is 1.0 times 10 to the minus x, in this case x is 4, the pH is 4. So that's our pH, but we're being asked, is it basic, acidic, basic, or neutral? And you should know the following. You don't have to write it down, but I will. When it's 7, it's neutral. When it's less than 7, it's acidic. And when it's more than 7, it's basic. And I see a question, so I'm going to take a second, maybe a little more than a second. And the answer is yes. Let me finish this and I'll scroll back up and go through it. So pH is 4, it's less than 7, so this is acidic. All right. Jada, do you need step 1 or 2 to be seen? You're welcome. And let's go through this again. You're being asked to find pH. You're not given hydronium, you're given hydroxide. Important information, you're given pH equal minus the log of the hydronium. And also Kw, yay, after me, not really, is hydronium times hydroxide equal 1.0 times 10 to the minus 14. You need to do 2 steps. This is an important information. Test number 4. Step 1, hydroxide to hydronium. This is chapter 7 for those who are wondering. Acids and bases. Step 1, go hydroxide to hydronium. Use this equation, what Kw is equal to. Solve for hydronium. Put the numbers in, you get this number. However, this is hydronium ion concentrate 3O plus. You want to go to pH, H3O plus to pH. Important information, pH equal minus log of hydronium. Put it in, you get 4. Your acid is acidic or basic. When it's less than 7, it's acidic. When it's equal to 7, it's neutral. When it's greater than 7, it's basic. And did I time it good or not? It's time for a break. Come back in 5 minutes and we'll continue on. I'll see you in 5. Uh-oh, I'm running late. Better get going. Let's continue with acids and bases. By the way, tomorrow I will go through the acid and base problem set. All right, I've already covered this. Well, let's go through it again. Acid-base titrations. That's a neutralization reaction in which a measured acid, volume of an acid, or a base of known concentration is completely reacted with a measured volume of an acid or base of unknown concentration. And by doing a titration, you can find the molarity of the unknown acid or base concentration. Now, we use what's called an indicator, also known as a pH indicator, which you saw if you've done the Beyond Lab Z Lab. Remember, that's due tomorrow, changes color. And the most common is phenolphthalein, which changes color at pH 7. And I'm going a little faster because we've already touched on this, but I want to do it once more. And titration data are used to calculate the molarity of the unknown acid or base. At neutralization, you calculate moles of known molarity or acid or base, and based on this, you can determine how many moles and therefore the molarity based on the volume. All right, when you do a titration using a pH indicator, when the pH indicator changes color, you're at neutralization. What does that mean? You're at pH 7 when using phenolphthalein, and that tells you moles of acid equals moles of base. And what that really means is milliliters of acid times molarity of acid equals milliliters base times molarity of base. And in titration, you have milliliters of both acid and base, and you either have molarity of acid and you solve for molarity of base, or you have molarity of base and you solve for molarity of acid. And this will be given to you in important information test number 4. In fact, let's find out if I'm lying to you. I don't think so, but never hurts to find out. And notice, does everybody see on your screen important information? Make up thumbs, people. Come on, you guys are slow. Maybe you can't see it. And you can't. How can you see it? Yeah, sorry. Everybody see important information? Thank you, Rain. All right, now for titrations, notice this is important information. At neutralization, you know this and you know this. So based on those things, let's get back to work. Wow, that's a lot to write. If it takes, everybody see 10 points on your screen? Uh-oh, I better check. Yes, you do. All right, if it takes 352 milliliters of a 1.05 capital M HCl solution, remember capital M molarity, to neutralize 175 milliliters NaOH solution, then what is the molarity of the NaOH solution? So what are we trying to find? Molarity NaOH. What are we given? By the way, this is a base. You should know that. You should know HCl is an acid. And we're also given how many milliliters, 175 of the NaOH solution we need or we have. And don't forget that's still a base. So what do we do? It's a titration. Moles of acid equals moles of base. And if you look at important information, test number 4, I give that to you. And the next step you should know is this: milliliters of acid times molarity of acid, milliliters of base, molarity of base. Now I'm going to put the numbers in. We have 352 milliliters of acid, that's HCl, right up here, times the molarity of the acid here. We have 175 milliliters of the base times we're trying to find the molarity of the base. And now we solve for this. How do we solve for this? we get rid of that. How do we get rid of that? Divide both sides by that number, because anything divided by itself equals the number 1. This cancels out. I'm left with don't forget, show your work on a test. Now, I like to rewrite it. You don't have to, but I do. And good habits I don't change. Notice milliliters left out. I'm left with molarity, which is what I'm trying to get. And now pick up my calculator, turn it on, clear it. Then my calculator gives me this number. But this is 3 significant figures. Oh, I'm in my rut. 3 significant figures and 3 significant figures. So I'll let you round this off to, you're right, 3 significant figures. Keep the 2, keep the 1, keep the 1, use 2 to round off. It's 4 or less, drop it. So the correct answer is 2.11 molar NaOH. And that's how you use titrations. And tomorrow's lab, you'll be titrating an unknown solution with either HCl or NaOH and doing this. And that's how you do titrations. Tomorrow, I'll go through the acid-base problem set. I highly recommend you work on this and know how to do that. And remember, you're trying to find the molarity. You're given this, you're given this. At neutralization, you know this, which then means this. And now you put in the numbers, solve for what you're trying to find by dividing both sides by 175, do the math, and that's how you do it. Now, let's talk about something very interesting, and that's buffers. And buffers is a solution that resists major changes in pH when small amounts of acid and base are added to it. In other words, the pH really doesn't change. And buffers, which you don't have to know, but are acids and their conjugate bases of weak acids. So when you have a buffered solution, if you add a small amount of an acid or base, the pH does not change. You should know this. Hint, a buffer is not the definition, but be able to apply it. A buffer is a solution that resists major changes in pH when small, and that's the key, small amounts of acid or base are added to it. Hold on, time out for a spelling check. Oh my God, I was right the first time. Sorry about that. In case you haven't heard, I was always down, first one down in any spelling bee. And I blew this one. I had it right. All right, now I've finished. 2 points each. What happens to the numeric value of the pH of a buffer solution? And that's the important thing. Buffer solution, when you add a small amount of dilute, and notice small amount, and dilute HCl. Don't forget, HCl is an acid. And the answer is when you add a small amount of acid or base to buffer solution, there's no change in the pH or very little change for this class. I'll call it no change. And B, when you have a buffer solution and you add a small amount of dilute and NaOH is a base, what happens? Buffer solution, small amount of acid or base, no change in the numeric value of the pH. And if you see on your screen, not to scare you, but I will. But anyways, everybody see, human blood contains a buffer. And guess what? That buffer solution keeps you between a very narrow range of 7.35 and 7.45. If you go higher than that, like higher than 7.8 or lower than 6.8, guess what? You're dead. So why learn about buffers? It's in your blood, it's keeping you alive. And that's important because your blood, if the pH is too high or too low, or too low or too high, whichever way, I'll do it this way, too high or too low, guess what? Oh, you are dead. So our buffer solutions Important? Yes. I love doing that. Buffer solutions, that is. All right. Wrong thing. Oh no, look what it says. It's the end of this chapter. But before we end this chapter, I have to tell a story. It's time for Dr. White's story. I don't think I told this. If I did, somebody raised their hand and say you told it. I know I told it in the other class I teach at the other school. All right, when I moved into the house I live in now, uh, after about a couple of weeks living here, my kitchen drain was stopped up. It barely drained. I figured, what did the previous owners dump down there? Because I'm very careful. Don't, when in the kitchen, put down any fat or grease down there. It'll clog up your drain. And being an organic chemist, I know that real good. So I called up my local rotor rooter man. He came out, did his thing with his rotor rooter, and it unclogged it. And I thanked him, paid him. I had a 6-month warranty or guarantee, whatever. And within about 2 weeks or less, it's clogged up again. Now, at that point, I'm working at a company where I have to go to work. So the money isn't the problem. It's me. I have to stop and stay home from work for wait for this guy to show up. I got a lot to do at work. I was a senior manager at a major chemical company. And so he shows up, does the same thing. Within a week, plugged up. I'm not a happy camper, which is not a good thing, but all right, I called him up. He apologized. Third time, he brings this bottle of stuff. This will clean it out, and I'll rotor rooter. I said, give me the bottle. I'm an organic chemist, who knows? And I'll teach this in a little while this week. Surfactants. It's an area I've worked in. I looked at the bottle and looked at the label and said, this ain't going to do much. It's more show and tell, not going to get the job done. But he did it, unplugged it within a couple of days, plugged up again. I'm not putting anything down there but water and soap and stuff and hot water. And that's probably part of the culprit, but there's still a lot of gunk down there. So I said, I'm not going to waste any more time calling this guy, forget about the money. So what do? I go to my local Home Depot, and I'm not getting kickbacks from them, but it's a really good one by my house in the Schaumburg Hoffman Estates area. And I have a whole wall of drain cleaners. And I asked, I'm looking at them, I'm picking up some bottles, and what the heck's the difference? And when a nice gentleman, and there are a lot of nice women who work there too, comes up to me and, can I help you, sir? I said, you work in this department? He says, yes. So all the drain cleaners up in this wall, it's like 5 shelves, it's like 10 feet long, it's huge. Which ones do the plumbers use? And I'm like, that. He says, that one. Which one is that one? Well, let's find out. All right, thumbs up, people. You see the black bottles that have the red hair and grease, says Instant Power. Thank you. And he pointed to this stuff. Now, this stuff, of all the bottles on that shelf, lots of them, different brands, was the only one in a thick, heavy plastic Ziploc bag that had on the outside of the bag in red letters, please use safety goggles when using this product. And I looked at the label, and let's see if I can do this. And if you look here, it says sodium hydroxide and potassium hydroxide are the two main ingredients in hair and grease remover. Hopefully you can all see that, and you should. So I read that and I go to the man and say, oh, it has a base in there, or bases. And he looks at me and says, no, those are acids. I said, sir, I have a PhD in synthetic organic chemistry. I know an acid from a base, those are bases. And he said, no, those are acids. Immediately I realized, why am I arguing with someone in Home Depot when I have a PhD in organic chemistry and know those are bases? He helped me, thank him, get it, go home and see if it works. So I thanked him. I went home, followed the instructions, except I let it sit in there instead of 15 minutes because it was real bad. I think I let it sit 45 minutes. I wore safety goggles just to be safe because the eyes are have to, and whenever you're dealing with hazardous chemicals, you should do that. I put on rubber gloves. I also have a lab coat, or you could wear a long sleeve shirt to protect in case something bad happened. You never know. And I followed the instructions other than letting it go. And lo and behold, clean drain. And I just to be safe, I did it a second time. And for about 12 years, nothing. It slowed up, never really stopped up. And I keep a bottle of that stuff, a big bottle, if I don't need to, and poured some in, no problem. Now, it also works in the bathroom for hair that, not that I have to wear, I don't have that much to lose, but if you have a stopped up drain in the bathroom, hair is one thing. Another thing I'll teach you about too, but mainly hair stops up a drain. And I've had students and my brother-in-law use it, works like that. About almost 6 months ago, my bathroom sink in my main bathroom up here, it's over that away, was starting to stop up. I said, oh, it's time to get the hair and grease remover out. And guess what? Boom, it's like brand new. Actually, I should have done it years ago because it's better than it's, even when I moved into the house, it's even better than that. And I also, for safe, uh, not safekeeping, but good practice, I did my bathtub too. That's clean like a whistle. Well, I don't know, is a whistle clean? Hold on. That's clean. All right. Story is use that product. I've used it. A lot of my students have used it. Friends and family have used it. It works. Be careful with it, but it works good. And you don't have to wait around for someone like the Roto-Rooter guy who really can't fix the problem that could. The other thing I learned is don't argue chemistry in Home Depot, even when you have a PhD in chemistry. It's not worth it. Don't. Once, a couple years later, when I was picking up some, those little white pellets, calcium chloride, because they were going to have real bad ice storm coming, a guy was buying something else, and which was, I'm going to sneeze again. It's a slow developing sneeze. It's slow sneeze Monday. But anyways, he was buying a product that was 50% sodium chloride, 50% calcium chloride, and I think it was a 50-pound bag, was cheaper than what I was buying, 50-pound of all calcium chloride. Calcium chloride melts things better at a lower temperature. He said, no, buy this, it's cheaper. I said, but this does better. He started arguing with me, not arguing mad, but no, this is better, it's cheaper. And I said, all right. And he went away. I bought what I want. And I finally realized, get it in your brain. Do not ever again debate chemistry in Home Depot. Not worth it. But at Home Depot and Menards too, they're very friendly, and also Lowe's, not to leave them out. All right. Any questions about acids and bases? All right. Well, it's time to talk about organic chemistry. which I'll be talking from chapters 9, 10, 16, 17, and 18. Now, I should tell you a couple things. One, you're on my home court now. I'm an organic chemist. Two, in a couple hours, I'm not going to teach you all of organic chemistry. Right now, I'm finishing up the last week at the other school of an 8-week summer, which is at COD I've taught, and at Elgin Community College I've taught a 16-week semester survey organic chemistry, and that just touches the surface. Any topics I talk about right now, I could probably do a whole year semester graduate level courses, but we're just going to give you enough, but it will help you learn about organic chemistry, and it'll be on test 4 and the final. Isn't it nice how I make things relevant? Points, I want it. All right, let's talk about organic chemistry. What's organic chemistry? Before I answer that, thumbs up. How many of you have heard about organic food? Guess what? Really, organic food, that term organic, has been hijacked by marketing, sales, mainly marketing departments of various food companies to mean, ooh, this is insecticide, pesticide, and other harmful chemicals free. In reality, all foods are organic, except now we're using that adjective organic foods to mean something for salespeople or to get you to buy some. But what does the word organic mean, or organic chemistry? Well, initially, organic chemistry got its name from study of molecules that were in living things like plants, animals, and us, humans. But about 1808, a German chemist made an organic molecule from something inorganic, from molecules that didn't come from things that were alive. And that means you had to change what is organic chemistry. And now organic chemistry is the study of molecules containing carbon atoms and other atoms, mainly hydrogen, oxygen, nitrogen, and other things too, but mainly those. Now, there's something special about a carbon atom. A carbon atom has 4 valence electrons. And you learned that earlier. Remember, valence electrons are the outermost electrons of an element. And because of this, and this is the amazing part about carbon and why it's my favorite element on the periodic table, well, I'm an organic chemist, it can bond to other elements, and this is important, including itself. It can form long chains with and without, and I'll teach you this, branches or rings. And it's the basis for all life on Earth. If we didn't have carbon, we wouldn't exist the way we do today. Would we exist at all? Good question. I don't know. Now, when we talk about carbon, your skin is made up mainly of carbon atoms with hydrogen. Your skin is a huge organic molecule. My cotton shirt, organic molecules. My hair and beard, what's left of it, is organic molecules. And most things are. Piece of paper, organic. Plastic pen shell, organic. My monitor, mostly organic molecules. Not the water in here, but the plastic bottle. That's organic chemistry, organic molecule. It's everywhere. And you know who's the greatest of all organic chemists? Mother Nature, and I mean that sincerely. The stuff she's done is amazing. your skin, your hair, cotton for your clothing, a whole lot of things. Just look at trees and anything growing outside or inside your house. If you got plants or animals or us, that's all organic chemistry. Now, there are a couple of definitions I would like you to know. And if you've been following the discussion about pollution and climate change, these play an important role, not the only role, but an important one. And the first one is hydrocarbons. What are hydrocarbons? Those are molecules with only carbon and hydrogen atoms. So if I say they're hydrocarbon pollution, I'm talking about molecules that only have carbon and hydrogen atoms. And that is a source of pollution that's causing global warming, hydrocarbons. Now, when we talk about hydrocarbons, there's two types. The first type we call saturated hydrocarbons. If it's a hydrocarbon, that means it's a molecule with only carbon and hydrogen atoms. And it also means in which all carbon bonds are single bond. Remember, single bond, one pair of electrons, double bond, two pair, triple bond, three pair. So saturated hydrocarbon is a hydrocarbon, meaning a molecule with only carbon, hydrogen atoms, which all carbon atoms are single bound or single bonds. Now, the other type of hydrocarbon is unsaturated. Unsaturated hydrocarbon, it's a hydrocarbon, so it's a molecule that has only carbon, hydrogen bonds, atoms, but now it contains, and this is important, one or more carbon-carbon multiple bond, which we mean a double bond or triple bond. So unsaturated hydrocarbons have carbon hydrogen atoms, but a double or triple bond and also carbon-carbon single bonds, but a saturated hydrocarbon has only carbon-carbon double bonds and it has only carbon hydrogen atoms. How many of you have heard of saturated and unsaturated fats and oils? No one? Nobody's heard of unsaturated fats? Why? You got at least one, two, some of it. Is this, I don't want to use my thumbs up Monday? All right, now, the same thing, and I'll teach you later on. Saturated fat has only carbon-carbon single bonds in a fat or oil, like vegetable oil, or unsaturated fat or oil has at least one carbon-carbon single bond. And I'll go over that later on. A triple bond is something, carbon-carbon triple bond is something organic chemists came up with. In all of the stuff Mother Nature did, she's never created a molecule with a carbon-carbon triple bond. Now, nitrogen has a triple bond, she did, but not organic molecules. Interesting, but true. So there's hydrocarbons, molecules with only hydrogen carbon or carbon hydrogen. There's two types that you should know. Saturated hydrocarbons, because it's a hydrocarbon, it has only carbon hydrogen atoms, but because it's saturated, all carbon-carbon bonds are single bonds. Now, unsaturated hydrocarbons are molecules, again, because it's a hydrocarbon with only carbon hydrogen atoms, but because it's unsaturated, it contains one carbon-carbon double bond or triple bond, or more than one. Now, one of the most amazing and powerful and wonderful things about organic chemistry is what we call functional groups. I'll never ask you what a functional group is, but it's a specific group of atoms in a molecule. And the beauty, and it is beautiful, now you know I'm an organic chemist, functional groups, if they're in one molecule or a different one, when you react it with a certain reagent, it always undergoes the same type of chemical reactions. And that's why we learn functional groups in organic chemistry, because those are the key parts of a molecule that we use to make new things. What new things? Well, did you wash your hands in the last day? I hope you did. The soap you use, whether it's bar soap or liquid, was made by organic chemistry using functional groups. The food you eat that Mother Nature did was made by using functional groups to make bigger things. When you chew and swallow and it goes in your stomach, the functional groups in your food are broken down into new molecules to help your body grow. Now I'm way beyond my knowledge of the human body to do things. And that's all functional group chemistry. What's a functional group? Now I'm going to come back to this slide. Now, again, functional group reactions are a reaction of a certain type of functional group to yield the same kind of product most of the time. There are sometimes exceptions. By the way, the letters I.E is Latin for that is. Now, this is important. How to find a functional group in a molecule. Look for anything that's not a carbon atom or a hydrogen atom or carbon-carbon single bond, and that will be a functional group. And that's where the fun is. That's where all the action is. So how do you find a functional group? Look for what's different in a molecule. What's not a carbon atom, a C, hydrogen atom, H, or a carbon-carbon single bond. So let's back up. Now, there are a whole bunch of functional groups. And the first one is the double bond. And a double bond in organic chemistry, we don't use Lewis structures. We use what's called the line structure, which I'll be teaching you. Now, a double bond we show by two lines. And one other thing I'll be teaching you in a little while, but I'll mention it now. There's always 4 bonds to carbon. I teach this organic, always 4 bonds to carbon. Does this look like it's coming at you? 4 bonds, 4 bonds. I'm an ambidextrous, so I can do it with both hands. There's always 4 bonds to carbon. If you find a difference to that, let me know. We'll be rich beyond my wildest dreams, which is beyond my own Lamborghini and Ferrari, beyond that, beyond my own fighter jets to play with, and beyond my own islands in the South Pacific. Much more than that. What I'm trying to say is it doesn't happen. There's always 4 bonds to carbon. All right, let's look at something. When I teach organic chemistry, I tell students to ask the following question. Why are you learning this? Or you should ask, why am I learning this stuff? Well, the obvious answer is when you take organic chemistry, you want to get a good grade in that class because somebody told you you needed to take it to get into a program or a school. Organic chemistry classes are required for like nursing. But really, why should you learn it? Let's look at one. Let's look at double bonds. But first, I've got to ask a question for all you thumbs up people. How many of you have seen a carrot or a slice of carrot in your life? Oh no, I mean, you haven't seen a carrot? You don't know what a carrot looks like? All right, some of you are being honest with me. Well, thank goodness for Google. All right, can everybody see carrots on your right side of the screen? For those who've never seen a carrot, look what color it is, orange. Why is that orange? Ooh, it's because of the following molecule. Now, the molecule that makes carrots orange is called beta carotene. Does everybody see all those lines on your screen now? Thank you, Ashley. Right here, each bend in the line is a carbon, each end of the line is a carbon. And where you see two lines, like right here, here, or here, that's a carbon-carbon double bond. And this is called beta carotene. How it got that name? That's called the common name, not an official, which I'll teach you, IUPAC name. But beta carotene has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 double bonds in it. And it absorbs all the colors of the light except the ones that make orange. And that's why carrots are orange. Now, your body breaks down beta carotene to make another molecule that has a common name called retinal. Sounds like something in my eye. It is. Your body uses retinal for your retinas, help you see better. And that's why Bugs Bunny sees so well, because of all the carrots he eats. How well those carrots help your eyesight? Don't know, but are there other sources of beta carotene? Yes, but I can't think of one right now. Carrots are the best. So when they say carrots are good for your eyesight, there's a fact behind that. Double bonds. So why are you learning? And that's a functional group. Boy, time flies when we're having fun with pH titrations and organic chemistry. And it's time to take a break. Come back in 5 minutes, 10:50, and we'll continue. Time to get going. Let's get back to organic chemistry. You know, I like what I've taught before, but this is the fun part of chemistry, organic chemistry. Now, we're talking about functional groups. How do you know a functional group? You look for what's different, what's not a carbon or hydrogen atom or carbon-carbon single bond, and that's where the fun is. Yeah. So let's look at some other functional groups. I just want you to get a feel for it. I'm going to skip triple bond. Now, you've heard of the term alcohol. Now, in gasoline and hard spirits, this you don't have to write down. This is called ethanol. This is an alcohol. And how do you know? Look for what's different. Oxygen with a hydrogen and a carbon, alcohol. Now, we have what's called aldehydes and ketones, also carboxylic acids, carboxylate anions, esters. By the way, esters look something like this. And we don't show, or we don't use in organic chemistry empirical formula like how many carbons, hydrogens, and oxygens. We show the structure. And this molecule has a common name, ethyl acetate. And it's one of the two molecules used as nail polish remover. And the other one, if I scroll back up to ketones, is this molecule. And this is called the common name, acetone. And this is also nail polish remover, and it's used for other things too. Now, a couple years ago, one of the things Dr. White likes to do is I go in a big box store, Target, Walmart, or other places. I'll look at certain areas to see what's being sold. And if you go to the part of nail polish remover, notice I have my nails actually, when I was a kid, men used to, 5 or 6, use a clear coat when you go to the barber shop, have a manicurist put it on. My grandfather did, my brother-in-law did for a while. But anyways, a couple of years ago in one of the organic chemistry classes I taught, either was here or at COD or at Elgin Community College, ECC, I said the main one, if you went into the most stores, most of the bottles on the wall for nail polish remover were acetate or ethyl acetate because it didn't burn the cuticles if you had any and smelled nicer than acetone. However, a couple of years ago, guess what? Ethyl acetate was replaced by mostly acetone. And one of the students told me why, or actually more than one. How many of you are familiar with the nail polish that you put it on, then you put your fingers under a light to harden it, which we call curing it? By the way, nail polish is sophisticated organic chemistry. And yes, Rain, it's called a resin too. I didn't know that. In terms of chemistry, I know resin, but nail polish. And because of that, you have a much stronger, more long-lasting nail polish on your nails. Well, ethyl acetate doesn't remove it as well as acetone, and that's why acetone made a comeback. Now, all your perfumes, most of them are esters, not ethyl acetate, much more complex esters. The next time you smell a flower or taste a fruit or smell a fruit or taste many vegetables or smell them, you're smelling an ester. Mother Nature does some amazing thing. Perfume is a complex mixture of esters mainly. to give you different effects. I don't know if that's the right word, the way a perfume smells. By the way, my mother's favorite perfume was Chanel No. 5. If you're not familiar with it, it's very expensive. In fact, do I have time? I do. I should cut this out of the video, but I won't. When I was in high school, I had a very good talent, and some of my other friends did too. I could get my mother upset with me like that, just say the wrong word, and boy, was I in the doghouse. For those who don't know that term, that means I was in not trouble, big trouble. And my father would come home from work. My mother would be really upset with me. My father would come to me, and I was very close to my father, and say, "All right, what'd you do now?" And he gave me that look like, "Oh, come on, how could you be so dumb and do that?" "Well, it just happened, Dad." He said, "You know what you got to do." I said, "Yeah." And I'd go over, and this is the one we lived in, Lincolnwood, next to Skokie. And in Skokie, there's a place, and it's still there, called Old Orchard. I think they changed the name slightly, but everybody knows that it's a huge shopping center, one of the original big ones in Chicagoland. And back then it was Marshall Field's, now it's Macy's. And I go to the perfume counter, which was quite big. It's a good size Macy's and then Marshall Field's. And the women behind the counter, after a while, would know, "What did you do now? What'd you say to your mother?" Because they knew I was there to get a bottle of Chanel. And the bigger the bottle, the more problems I had, and the bigger it had to be. And it always worked. Gave her a bottle. "All right, you're forgiven." But I had that talent. And the women, after a while, by my senior year of high school, if I was walking up to the counter, one of the women would look at me and say, "Did you get your mother mad at you again?" "Yeah." "How big a bottle do you want?" They already knew what I was going to buy. Luckily, later on, I learned not to do that as badly. And other functional groups, let's look at quaternary ammonium salts. Now, quaternary ammonium salt, and there's shorthand, we do certain organic molecules. Our sub T means 18 carbons and hydrogens. This is a quaternary ammonium salt. Why did I draw that? That quaternary ammonium salt, called dimethyl ammonium chloride, was, until about 10 years ago, the only molecule used for fabric softener. And Dr. White's worked in that area. In fact, in quaternary ammonium salts, I have 9 US patents. So I know about it? Yes, I'm a world authority. And quaternary ammonium salts has got me around the world. It's paid for cars, it's paid for my mortgage, a whole lot of other nice things. And I know quaternary ammonium salts. So what am I teaching you? When there's a functional group, you look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom. That's a functional group. And that's where the fun and action is. Oh, I should mention this. When you take organic chemistry with me, Dr. White, unfortunately, I don't teach it at COD anymore, political reasons I'm not going to get into. I still teach it every semester at college, Elgin Community College. The math is horrendous. Not really. You have to know how to add and subtract up to 4. You have to know first part of the semester through week 12 how to count up to 10 and know which numbers from 1 to 10 are bigger and smaller than the others. Later in the semester, you have to know how to go up to 20. And that's it. That's the math for organic chemistry. But there's a lot of memorization. So in certain ways, it's harder than this class. In certain ways, it's not. Now, Functional group reactions, it's a reaction of a certain functional group to yield another certain type of product, another type of functional group, and it's mostly this works fine. There are exceptions like there is in life. Now, functional groups. Again, how to find a functional group in a molecule. Look for anything that's not carbon atom or hydrogen atom or carbon-carbon single bond. Oh no, you know what time it is? It's, time for me to close something and hang in there. Nope, it won't even let me save stuff. All right, sorry about that. Every once in a while, I've got too many things open on the computer. I've got a lot of things running on it right now. It doesn't like what I'm doing. All right, we're talking about functional groups. And let me make sure you can still see it. All right, for a functional group, look for what's different. Look for anything that's not a carbon atom or a hydrogen atom or carbon-carbon single bond. And guess what? It's time to play that fun game. Circle the functional groups 2 points each. And how do you play that game? Circle the functional group 2 points each. I make sure you can see it. You can. Let's look at the following. Does everybody see the molecule A on your screen? Let me make sure I can see that you seeing it. Thumbs up, people. Can you see the molecule on your screen? Thank you. All right. How do you play that fun game? Circle the functional groups 2 points each. You'll look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom. That's going to be a functional group. And notice here we got an oxygen, a chlorine with a hydrogen. And I'd circle that. It's called an alcohol. This is an alkyl chloride. And that's how you play that fun game. Circle the functional group, 2 points each. And why don't you try B and C? Take each one, and I'm not asking you to name it, the circle the functional group or groups in each molecule. 2 points each. B is 2, C is 2 points. And have fun playing that fun game, circle and name the functional group, 2 points each. And just click on yes if you're done. You don't have to know. Let me see when a majority of the people are done. Remember, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom. That's where the functional group is. Love that whistle. When I look at molecules, this is the first thing I do. I scan real quick, look over what's different, because that's where the functional groups are. That's where all the fun and action always is. All right, let's take a look at this. And the question is, circle the functional group, 2 points each. And notice, oh, a double bond. And that's one of the functional groups. That's different. One line is a single bond. In organic chemistry, 2 lines is a double bond. And 3 lines, which I don't show here, is a triple bond. Oh, look, a bromine. That's a functional group. And notice oxygen and it's double bond to carbon. That's called a carbonyl group. And this is a functional group called an aldehyde. So that's what you should have circle. Oh, look, a nitrogen. That's different. That's a functional group. Ooh, an oxygen. And that's different. By the way, carbons, and we use the letter R like math people use X and Y. This is called an ether. And I'm going to turn the switch off, but ethers are important. One of the most famous of all ethers is this molecule. You don't have to write it down. And ethers, this is called ethyl ether, and so famous, some people just call it ether. When they say ether, you know they're talking about this molecule. Now, that molecule is very flammable. Ethers, small ones, are very flammable. They make gasoline look like water. But interesting thing, about 1835, give or take 5 or 10 years, medical science found out that if you had someone inhale ethyl ether, it put them out, knocked them out. And guess what? You could operate on them. And unfortunately, in the American Civil War, 1860 to 1865 approximately, a lot of people, men, were severely injured from the battles of our Civil War, bloody war, and they had to be operated on. And ether was used. There's one problem, it's flammable. And if you were having someone with a oil kerosene lamp near while they're doing surgery, guess what? You're going to have a fire. And later on in the 1900s, early 1900s, if you're using electricity and had a spark to cauterize a blood vessel, close it up, and the person had ether in their mouth, their lungs, guess what? You had a fire and a dead patient. And a lot of times you had a surgeon whose hands were burned and no longer could be a surgeon. Well, they found out by replacing some of the hydrogens in on ethers, it wasn't flammable. And switches off, but thumbs up, people. Do you see the Wikipedia for isoflurane? And if you look over on the left, on the right, you'll see F is fluorines. Each bend in the line, each intersection is a carbon. Carbon here, oxygen, carbon here with two fluorines and a hydrogen. You don't show hydrogens. It's called line method. This is used today as an inhalation anesthetic. Do I have time? Oh, I do. Look out. Now, isoflurane is not as flammable. When you replace the hydrogens with halogens, it's much, much less flammable and safe to use. Now, years ago, when I moved into this house, I did something dumb. Yes, I can do those. And what was it? It was that I was moving boxes of books and I forgot to put, or I wasn't smart enough to put on a weight belt, which I own. And I was picking up 100, 150 pound boxes, carrying them upstairs, 5 or 6 steps. Guess what? I popped my hernia and I had to have a hernia operation. Went to my doctor and he said, you need an operation soon. And luckily, my brother-in-law's best friend had used this great surgeon who was a heart and regular surgeon too. And I went to him and said, yeah, you need it. And he said, I think the other side is going to go too. I really need to go in there. So great surgeon, but I didn't know something about him. Well, I went to this really fine hospital in Evanston where he operates out of. And my surgery was supposed to start at 1 o'clock. So I get there around noon. You know how if you've ever had surgery, they put you in a surgical gown, they make you lay down in a gurney, and they push you to the operating room. And it's about 5 to 1. I'm laying on my back. There's a big clock over here. I'm not in the operating room. It's 1 o'clock. It's 5 after 1. It's almost 10 after 1. And one of the nice doctors who was going to be in the surgery, mine, had the mask on, the hat and the gown and gloves, comes up to me and says, I see you're looking at the clock. You don't know something about your surgeon. My eyes go, what? What? He said, relax. He's never on time. He never, he's great, but he's never on time. And he said, hey, he told me, I'm your anesthesiologist. And he says, I said, oh, I'm an organic chemist. What are you using? So he brings over one of the bottles and it was the isoflurane. And he says, this is what we're going to use. And I said, well, it has this structure. And he said, oh, I got to get to work. What's wrong? Well, can't you tell your surgeon was arrived? How can I tell? I have a mask on. Anyways, it was major surgery. I was in the operating room for 5 hours That's how bad the reconstruction was. And he did a great job because I've never had a problem. That was over 20 years ago. And he said within 10 or 12 years, you may have to have this fixed up, but I don't think so because I really reinforced it. But it was 5 hours of surgery. It was really something. In case you're wondering, I survived. I'm healthy now because of that. But that was an ether and organic chemical. Oh, let's play a couple more, at least one more. And let's do D. Circle the functional group, 2 points each. Have fun. Remember, a functional group, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. And that's where the fun is. Pro tip, look for what's not the letter C or the letter H. That's where the fun is. Remember, tomorrow, besides our lab, we'll do another Beyond Lab Z lab. It's going to be fun. Don't forget, hand in the lab, that's due tomorrow. And I'll also tomorrow be going through the acids and bases problem set for test number 4, which is coming up soon. All right, I think everybody's done. Let's take a look. Ooh, an oxygen. And here's our functional group. Ooh, nitrogen. Here's another one. This carbon has 2 oxygens attached to it, and here's another one. This is called an alcohol. This is called amine. This is called an ester. I'm not asking you to learn that. Now, these are called structures. We don't do empirical formulas like H2O or other things. We in organic chemistry use structures, show that. You can do empirical formulas, but they're not helpful when you're trying to do organic chemistry. So, how do you draw organic molecules? Now, there are different ways. I'm going to be teaching you one of them, and I'll show you another two. It's called the condensed structures. It shows how atoms are connected, but we don't show carbon-carbon, carbon-hydrogen bonds, and I do just to keep my structures, and usually you don't show carbon-carbon single bonds. Other ones you don't. Now, there's another one with parentheses where it's the same as condensed structures, but use a pair of parentheses with a number to show a repeating unit of a molecule. All right, see board for examples. Before I do, how many bonds to carbon? You should know this. There's 4 bonds to carbon. How many? 4. Does it look like it's coming right at you? 4. And it is 4 bonds to carbon. 1, 2, 3, 4. Always. And that helps you learn how to draw. Let's look at a simple molecule. Actually, the simplest. Now, this is called the expanded view, which we don't use. Notice this has 4 bonds to carbon. 1, 2, 3, 4. Now, the condensed is on this carbon, how many hydrogens? 1, 2, 3, 4. So we write it this way. And this you should know how to do. By the way, I'm not going to ask you to learn this, but this is called methane. And you know it as natural gas. And if you cook at home, or your parents or whoever cooks at home with a gas oven or stove, you're burning this methane. If you have a hot water heater here in Northern Illinois, you're burning methane. And also in the winter, to keep your apartment, condo, or home warm, the furnace is burning natural gas methane. Now, how do you put in the hydrogens in this structure? And you should know this. Getting ahead of myself. How do you know how many hydrogens to put in? You count the bonds. There's always 4 bonds to carbon. Always. And now we're going to have to do some heavy duty math. There's always 4 bonds to carbon, and carbon has 1 bond. The remainder are hydrogens. There's always 4 bonds to, oh, my finger's broken. There, 4 bonds to carbon. Yes, 4. Oh, this one's broken now. 4 bonds to carbon. 4, 4. So if you have 1 bond, the rest are hydrogens. And that always works in. Count the bonds to carbon. And if you don't have 4, the remainder are hydrogens. So let's look at that molecule I had on the screen. And notice this carbon has 1 bond to it. And I'll show the lines. So how many hydrogen? Well, there's 4 bonds. There's 1 you see. So there has to be 3 hydrogens. Now let's look at the next carbon. This one. How many bonds do you see to it? How many lines? 2. 1, 2. But there's always 4 bonds to carbon, and that doesn't have it. Well, 4 minus 2 is, hopefully you got this right too. So I'm going to put 2 hydrogens there. Now, before I do it, I'm going to let you try the last carbon, this one right here. How many bonds do you see to that carbon? And the answer is 1. Well, there should always be 4 bonds to carbon, and the remainder are hydrogens if there aren't. So 4 minus 1. Yep, you're right, 3. And I could draw the molecule this way without the lines. And this molecule has a name, and we call it propane. And propane is the molecule you buy in those white tanks for your barbecue. And you burn this to cook your food. And that's propane. Now, since I'm a nice person, I have to share the fun. Put the hydrogens in for this molecule. Remember, there's always 4 bonds to carbon. Each line counts as a bond. So 4 minus the number of lines tells you how many hydrogens. Your turn, 3 points each. Put in the hydrogens for this molecule. Go. When you're done, give me a thumbs up, please. Or any other emoji. Remember, there should always be 4 bonds to carbon. And if they're not, the remainder will be hydrogen atoms. And when you're done, give me a thumbs up. And hopefully you won't have to use your calculator for this, but you can if you want. When I teach organic chemistry, I tell the students, you're not allowed to use a calculator. See how mean I am? They have to learn how to add and subtract up to 4. All right, I think some of you are still, well, I'll give you another 25 seconds, maybe 30. All right, let me do this. And I'm going to do another one, let you try it. Let's look at each carbon. We look at this one, there's 1 bond to it, but there should always be 4. 4 minus 1 equals 3. So there should be 3 hydrogens. If we look at this carbon, there's 1, 2 lines or 2 bonds to carbon. There's always 4 bonds. 4 minus 2 equal 3. Equal 2. Uh-oh. Just had a brain misfire. 4 minus 2 is 2. And we show that like this. Let's look at this carbon. How many lines or bonds do you see? One, two. There should be 4 bonds to carbon. Oh, somebody did on this already, right? 4 minus 2 means 2. And that's how you do it. Now we do the last carbon at the end on the right. And how many lines do you see of this carbon? 1. That's 1 bond to carbon you see, but there should always be 4. 4 minus 1 is 3, and we show it this way. And that's how you do it. By the way, this molecule has a name, and it's called butane. How many of you ever seen those small lighters or the bigger ones for your barbecue that are called butane lighters? Those plastic ones or the bigger plastic ones, if you look, you can see a liquid inside. And that liquid is butane, which is why they're called butane lighters. When it spark and air from the atmosphere, you get a flame. Oh, let's do another one. I think you could use to practice. And here's one for you to practice. Put in the hydrogens in this molecule, 3 points. Remember, count the lines to the carbon, and that tells you how many bonds. There should always be 4 bonds to carbon. 4 minus the number of lines tells you how many hydrogens you have to put in. I forgot to mention there was, I think, one perfect paper, and a couple of the students, your colleagues, got over 100. There's 105 max, 5 bonus points on test number 3. All right, let's do it. The question is, how do you know how to draw in hydrogens? There should be 4 bonds to carbon. If we look at the first one, there's one bond. So 4 minus 1 equals 3. And I show that by a hydrogen and subscript 3. This one, 2 bonds. Four minus 2 equals 2. I got it right this time. So there should be 2 hydrogens. Same with this one. Same thing, 2 lines, same here. Same thing here. Same thing here. Same thing here. And this one has 1 bond to it. 4 minus 1 equals 3. And this molecule is called octane. It's a saturated hydrocarbon. Why? Because there's only carbon-carbon single bonds and only carbon and hydrogen atoms. Now, how many of you have heard of the octane number, like in a gas station? I'm going to go to this view. Give me a thumbs up. Did your thumbs up emoji break? Nobody's ever heard of octane number? You know, when you go into a gas station, you have the different types of gasoline. They have what's called the octane number. And back about 1900, 1905, when cars were just starting to hit the road and gasoline was a new product, the gasoline with the most octane in it, the molecule you saw, or isomers of octane, ran the smoothest in a car engine. Later on, they found out how to add other chemicals we call additives to make your gasoline better for your car and help your car engine and your car mileage. But the octane number is still a good thing. The higher the octane number for higher powerful engines. I use the regular lowest one, but once in a while, I'll use the higher, more expensive. It's higher octane, better additives, helps clean your gas out, your car engine out. Now, I think I mentioned before, having worked for a company that sold additives to gas or petroleum companies, gasoline companies, the best gas is Shell. Mobil is just a little below it. Marathon is similar, quite good. And the worst is down in the underneath my house. That's how bad it is BP standard. I will never buy that unless it's an emergency and I need gas, which where I live, that's not a problem. So with that, I look at the clock and, oh no, time flies when we're having fun with organic chemistry and 4 bonds to carbon. I'll see you tomorrow. Don't forget the lab we did on Thursday is due tomorrow. How do you like that? Due tomorrow. Tomorrow's over here, yesterday's over there. And with that, I'm going to say, gang gesund, goodbye. Don't forget, if you have any questions about anything, come to my office hour tonight. Goodbye.